Every day, millions of people around the world add a spoonful of white crystalline sugar to their morning coffee. But that small, simple grain has traveled a remarkable journey before it ever reaches your kitchen. It has been cut, crushed, filtered, evaporated, crystallized, and refined through one of the most sophisticated food manufacturing processes in the world. In this video, we go inside a modern mega sugar mill, a facility that processes tens of thousands of tons of raw sugarcane or sugar beet every single day. Sugar production starts in the field, with sugarcane in tropical and subtropical regions and sugar beet in cooler climates. Both crops serve as the primary source of sucrose, the naturally occurring sugar that factories extract, refine, and crystallize. Whether the source is sugarcane or sugar beet, the destination is always the same: pure, white, refined sugar crystals of consistent quality delivered to tables around the world. In a sugarcane-based mill, large haul trucks and agricultural trailers arrive at the factory entrance loaded with freshly harvested cane stalks. The cane is typically transported within 24 hours after harvesting. At the intake area, each incoming load is weighed on large industrial weigh bridges, heavy-duty scales capable of handling fully loaded vehicles. The data feeds directly into the factory's production tracking system. For sugar beet operations, beets are delivered in bulk from surrounding farms during the campaign season. Upon arrival, beets are sampled and tested for sucrose content, purity, and the presence of impurities like soil and stones. These readings determine the value of each delivery to the farmer and set the processing parameters for the day. Even at this earliest stage, quality management has already begun. In the yard, powerful hydraulic tipping mechanisms tilt the delivery vehicles, and the raw material cascades onto receiving conveyors or into intake pits. Overhead cranes and grab buckets assist where necessary. One of the most important assets in a modern sugar factory is the storage buffer, a carefully managed stockpile of raw material that ensures the plant can continue operating even when deliveries slow down or temporarily stop. This buffer, combined with smart logistics scheduling, keeps the highly continuous production process from experiencing costly interruptions. Before the raw material moves further into the plant, it passes through a preliminary cleaning station. For sugarcane, mechanical dry cleaners use rotating drums and air jets to remove loose leaves, dirt, and field debris from the stalks. For sugar beet, large rotating drum washers with water jets scrub the beets clean of soil, which would otherwise contaminate processing equipment and reduce extraction efficiency. Cleaner material means better sugar. Even at this very first stage, quality is already being managed. Every step from here forward is designed to protect and purify the sucrose that will ultimately become finished white sugar crystals. Once the raw material is clean and prepared, the extraction process begins. This is the moment where the sucrose locked inside the plant cells is released and made available for processing. In a sugarcane mill, extraction is done through mechanical crushing. The cleaned cane stalks are fed into a series of large, heavy roller compressor rollers arranged in sequence, often 4 to 6 sets in a row. As the cane is crushed, a dark green-brown juice is released. This raw juice, called mixed juice, contains water, sucrose, and a range of impurities including organic matter, fiber particles, and various chemical compounds. To maximize the yield of sucrose extracted from the fiber, factories employ a process called imbibition. Hot water or diluted juice is sprayed onto the crushed cane fiber, called bagasse, as it exits each roller set. This water soaks into the remaining fiber, dissolving any leftover sugar, and the diluted juice is fed back into the earlier crushing stages for re-extraction. Through this, recovers nearly all the available sucrose from the cane. In modern mills, it is not wasted. It dewars where it is burned as fuel, generating the steam and electricity that powers the entire factory, making the milling process largely self-sustaining from an energy perspective. This makes the sugar milling process largely self-sustaining from an energy perspective, a remarkable example of industrial efficiency that modern factories have refined over decades. In sugar beet processing, the extraction method is different. Instead of crushing, factories use a process called diffusion. The cleaned beets are first sliced into thin strips called cosettes. These thin strips dramatically increase the surface area available for sugar extraction. A long, countercurrent extraction vessel, where hot water flows in the opposite direction to the beet material. As the water and cosettes move in opposite directions, the sucrose gradually diffuses out of the beet cells and into the water, producing a raw juice. Nearly 98% of the available sucrose has been removed. The countercurrent design ensures that the beet material always meets progressively cleaner water, maximizing the concentration gradient and the efficiency of extraction. Like bagasse in cane processing, the spent beet pulp is not discarded. It is pressed to recover additional water, then dried and sold as animal feed, a high-fiber, nutritious supplement widely used in agriculture. At this point in the process, the factory has produced raw juice, a slightly cloudy, greenish or brownish liquid that contains sucrose along with a complex mixture of non-sugar compounds that must now be carefully removed. Raw juice is far from the clean, clear solution that will eventually yield white sugar. It contains organic acids, amino acids, proteins, colorants, waxes, and colloidal particles, all of which must be eliminated before crystallization can occur. In the liming and carbonation process, carefully measured quantities of milk of lime, a suspension of calcium hydroxide in water, are added to the raw juice. The lime raises the pH, causing many impurities to precipitate out of solution. Following liming, the juice enters carbonation tanks, where carbon dioxide gas is bubbled through the mixture. The sulfonyl hydroxide that acts like a filter bed, trapping and carrying down many impurities. This mixture then proceeds to rotary vacuum filters, where the calcium carbonate precipitate, along with all the trapped impurities, is separated from the juice. The filter cake is continuously scraped off and removed. This filter cake, called press mud or carbonation lime, is typically used as a soil amendment in agriculture due to its calcium-rich composition. Nothing in a modern sugar factory goes to waste. What passes through the filter is a noticeably clearer, purer juice. Depending on the target purity level, this clarification stage may be repeated or supplemented with additional fine filtration steps. In some factories, an additional sulfitation stage is included. Sulfur dioxide gas is introduced into the juice to bleach colorants and further stabilize the sucrose. Its use is carefully controlled and monitored within safe and regulatory limits. At every stage of purification, laboratory technicians are continuously sampling the juice, measuring its purity, sucrose concentration, and the levels of specific impurities. This real-time feedback allows operators to adjust processing parameters instantly. After purification, the clarified juice still contains a large proportion of water, typically only 12 to 15% dissolved sugars. Before crystallization can occur, this water must be removed through the process of evaporation. The evaporation station consists of a series of large interconnected vessels called evaporators, arranged in a multiple effect evaporation system, a highly efficient design that uses the steam generated in one evaporator as the heating source for the next. In the first evaporator, live steam from the factory's boilers heats the juice. As the juice boils, water evaporates and is driven off as secondary steam. Rather than wasting this steam, it is fed into the heating chamber of the second evaporator. Because each effect operates at progressively lower pressure, and therefore lower boiling point, the same unit of steam energy effectively does the work of evaporation multiple times over. This dramatically reduces the amount of fuel required. A modern factory may operate 3, 4, or even 5 evaporator effects in sequence. As the juice passes through each effect, its water content decreases and its sucrose concentration steadily increases. By the time it exits the final evaporator, the juice has been transformed into a thick, viscous syrup called thick juice, with a sucrose content of approximately 60 to 70% by weight. This syrup is dark amber in color and has the consistency of a heavy, molasses-like fluid. It is now concentrated enough to proceed to the next critical stage, crystallization. Temperature control throughout evaporation is precise and critical. Too high a temperature can cause sucrose to break down into glucose and fructose, a process called inversion, which reduces yield and creates undesirable colorants. Crystallization is the heart of sugar manufacturing, the stage where dissolved sucrose transforms from a syrup into the solid white crystals we recognize as sugar. It is one of the most technically demanding stages in the entire process. The crystallization process takes place in large cylindrical vacuum vessels called vacuum pans. These vessels operate under reduced pressure, which lowers the boiling point of the syrup, allowing crystallization to occur at temperatures low enough to protect the sucrose from heat degradation. As the syrup reaches a specific concentration, called supersaturation, the conditions become favorable for crystal formation. At this precise moment, the next critical step begins. The operator introduces a small quantity of fine sugar crystal seed, either finely milled sugar or a prepared seed crystal slurry. These seed crystals provide nucleation points around which sucrose molecules begin to deposit and build up as orderly crystal structures. The art and science of this process lies in maintaining just the right level of supersaturation throughout the growth phase. If too high, unwanted crystals nucleate. If too low, existing crystals dissolve. The balance must be perfect. Modern sugar factories employ advanced automated control systems that monitor all parameters in real time and automatically adjust steam flow, vacuum level, and feed syrup flow. What was once an art mastered over many years is now guided by sophisticated algorithms. When the crystals have reached the desired size, the vacuum pan is discharged. The thick slurry of crystals suspended in mother liquor is transferred to a large holding vessel called a crystallizer, where it continues to cool under slow controlled stirring. This additional cooling crystallization recovers more sugar from the mother liquor before the final separation step. In large factories, multiple vacuum pans operate in a staggered cycle, ensuring a continuous, steady flow of massecuite. Once crystallization is complete, the massecuite must be separated. The crystals need to be isolated from the surrounding syrup, washed clean, and readied for drying. This separation is accomplished using centrifugal machines, one of the most visually striking pieces of equipment in the entire factory. Industrial sugar centrifuges spin at high speeds, typically between 1,000 and 2,000 revolutions per minute. When massecuite is loaded into the spinning basket, centrifugal force drives the liquid mother liquor through the screen perforations and out of the drum, while the sugar crystals are retained on the screen surface. The separation is remarkably fast and effective. Within minutes, or even seconds in the most advanced continuous centrifuge designs, the bulk of the mother liquor has been separated from the crystals. The retained crystal layer on the screen is then washed with a carefully controlled spray of hot water or steam. This washing step rinsing into the crystal surface, which would otherwise impart color and reduce the purity of the finished sugar. There are two main types of centrifuges used in sugar factories: batch centrifuges and continuous centrifuges. Batch centrifuges are typically used for the first crystallization stage, where crystal quality must be carefully managed. Continuous centrifuges feed massicrete in at one end and continuously discharge separated crystals at the other, making them ideal for lower grade stages where throughput is prioritized. The liquid that drains through the centrifuge screen, called molasses or green syrup depending on the stage, is not discarded. It is collected and returned to the process for further crystallization, extracting progressively more sucrose. By the third or fourth cycle, the syrup has become so depleted in sucrose and so concentrated in non-sugar compounds that further crystallization becomes impractical. The remaining dark thick liquid is called final molasses or blackstrap molasses. Final molasses is sold as a valuable co-product, used as animal feed, as a fermentation substrate for ethanol and rum production, and in a range of food and industrial applications. Wet sugar crystals emerging from the centrifuges contain a small but significant amount of residual moisture, typically 1 to 2% by weight. This moisture must be removed before the sugar can be safely stored or packaged. The drying process most commonly uses large rotary drum dryers, long, slightly inclined rotating cylinders through which the wet stream. A drum rotate, the sugar tumbles gently, presenting fresh, wet surfaces to the airflow. The temperature of the drying air is carefully controlled. Too high a temperature risks caramelizing the sugar surface, introducing unwanted color. Too low a temperature leads to insufficient drying. Modern dryers continuously adjust drying conditions automatically. Following drying, the sugar enters a cooling stage. The freshly dried sugar is still warm, and if packaged at this temperature, condensation could form inside the packaging, reintroducing the moisture that was just carefully removed. Cooling is achieved using rotary coolers similar in design to the dryers, but with ambient or slightly chilled air circulated through the tumbling sugar. This gentle airflow draws heat from the crystals without adding moisture. At the exit of the cooling system, the sugar passes over a set of vibrating screens. These screens separate any oversized lumps or agglomerated crystals that may have formed during processing. The sugar is now physically complete, dry, cool, free-flowing, and pure. But before it reaches any packaging line, it passes through one more critical checkpoint in the refining process. Not all sugar production follows the same path to whiteness. In some factories, the mill first produces raw sugar, a golden brown, high purity but still slightly colored product, which is then further refined into pure white sugar. The refining process begins with the affination step. Raw sugar is mixed with a small quantity of hot syrup to form a thick mixture called a magma. This magma is then centrifuged, washing away the syrup coating that carries the majority of the residual color and impurity. The syrup coating on the surface of the raw sugar crystals, which carries the majority of residual color and impurity, is washed away, leaving crystals that are pure and lighter but not yet the brilliant white of fully refined sugar. These affined crystals are then dissolved in hot water to produce a high-purity liquor. This liquor passes through a decolorization process, which removes the remaining colorants that survived earlier purification stages. The two most common decolorization technologies in modern refineries are activated carbon treatment and ion exchange resin treatment, both highly effective at removing the last traces of color from the sugar liquor. In activated carbon treatment, the liquor passes through vessels packed with granular activated carbon. Hydrant molecules are adsorbed onto the carbon surface as the purified liquor passes through. The carbon is periodically regenerated by heating it in a kiln, burning off exchange resins and synthetic polymer beads that selectively bind to colorant molecules and are regenerated periodically with chemical washing solutions. After decolorization, the liquor is filtered again through fine filtration systems to remove any residual fine particles. At this point, the liquor is exceptionally clear and nearly colorless, ready for the final crystallization stage. It then proceeds to a refined crystallization stage, where the same vacuum pan process used earlier is repeated, this time with the clear, decolorized liquor, producing the brilliant white, highly uniform crystals of fully refined white sugar. A modern sugar factory is as much a laboratory as it is a manufacturing plant. Quality control is not a final inspection step from the very first delivery of raw material to the last bag of packaged sugar. At the heart of quality management is the factory laboratory, staffed around a collaborative production process testing for sucrose concentration, color, turbidity, conductivity, moisture content, and pH. Before any batch of finished sugar is released for packaging, it must pass a final quality check. Samples are drawn from the product stream and analyzed. Only material that meets all specifications proceeds to the packaging lines. For sugar going to market, strict international standards define the acceptable limits for color, moisture, and ash content. The International Commission for Uniformly Recognized Colorless used to classify sugar grades. Lower ICUMSA numbers correspond to whiter, purer sugar. Refined white sugar for retail markets typically carries an ICUMSA rating of 45 or below, the benchmark of truly premium white sugar. Traceability is another cornerstone of modern quality management. Every step in the production process is logged with timestamps and instrument readings. If a quality issue is ever discovered, the factory can trace that material back through every stage of its production journey. Hygiene is maintained at the highest level throughout. Production areas are cleaned regularly using clean-in-place systems that circulate hot water and cleaning solutions through pipes and vessels without the need for manual dismantling. Once the finished sugar has passed all quality checks, it flows into large storage silos, typically tall enclosed concrete or steel structures with capacities measured in thousands of tons, designed to maintain the sugar in optimal condition. Within the silos, sugar is kept in continuous gentle motion to prevent bridging, the formation of hard crust that could block the outflow. Sensors monitor the fill level, temperature, a complete picture at all times.
From storage, sugar is conveyed to the packaging hall. A packaging formats varka to stereo in the high rates where the finished needs in dustbrokens alike.
For retail markets, automatic packaging machines fill and seal sugar into familiar 1 kilogram, 2 kilogram, or 5 kilogram bags that appear on supermarket shelves. Checkweighers at the exit of each packaging line verify that every single bag contains the correct weight, rejecting any that fall outside the permitted tolerance. Precision and consistency apply equally to weight as they do to purity and color. For industrial customers, large food manufacturers, confectionery plants, soft drink producers, and bakeries, sugar is packaged in bulk formats, large paper sacks, flexible intermediate bulk containers, or bulk tanker truck deliveries of loose sugar. Throughout the packaging process, automated systems handle most of the physical work. Robotic palletizers pick and stack silicone bags, and pallet wrapping machines apply stretch film to secure each load for transport. Automated labeling systems attach product labels, batch codes, and barcodes to every finished pallet. Finished pallet transport to the finished goods warehouse, where warehouse management systems track the location and status of every pallet. From the warehouse, sugar is loaded onto trucks, rail cars, or ships for delivery to customers around the world. A logistical operation requiring the same precision as the manufacturing process itself. A modern sugar factory is a complex energy ecosystem. The production process requires enormous quantities of steam and electricity. For Evaporation, Crystallization, meeting this demand efficiently and sustainably is a constant engineering challenge. Sugarcane-based factories are largely self-sufficient in energy. The gas is burned in high-efficiency boilers to generate steam that drives turbines producing electricity. Many cane mills export surplus electricity to the national power grid. Water management is a critical environmental consideration. Modern factories employ extensive water recycling systems, treating and recirculating processed water rather than continuously drawing fresh water from external sources. Wastewater treatment plants clean any discharge before release. Air quality management systems capture dust emissions from drying, handling, and packaging operations. Fine sugar dust is not only modern factories use enclosed conveyors and bag filters on all dust-generating equipment. The overall environmental footprint of sugar production has over recent decades, and its efficiencies of Filtration have transformed the industry into one that meets stringent modern environmental standards. From the moment a truck laden with freshly harvested sugarcane or sugar beet rolls through the factory gate, to the instant a neatly sequence of physical, chemical, and engineering process has taken place. Raw plant material has been cleaned, shredded, crushed, and pressed. Its juice has been extracted, purified through multiple stages of chemical treatment and filtration, and concentrated by evaporation through a carefully engineered series of vessels. Sucrose molecules, freed from the sugarcane or beet in which they were grown, have organized themselves into perfect, ordered crystal lattices. The bright, pure white grains of sugar we recognize. Those crystals have been separated by high-speed centrifuges, washed clean of any residual color or impurity, dried to the precise moisture content required for safe long-term storage, cooled, screened, and verified by the factory laboratory to meet exact international quality specifications. Throughout every stage, modern factories deploy an arsenal of sophisticated technology, precision sensors, advanced process control systems, robotic handling equipment, and analytical instruments that test dozens of parameters in real time. The result is a product of extraordinary consistency. A bag of white sugar produced today in a modern factory will have virtually identical purity to about per crystal size and elasticity. It is the product of decades of engineering refinement, rigorous quality management, and a deep understanding of the chemistry and physics underlying every step of the process. For all the sophistication of the machinery and the science involved, the fundamental goal remains beautifully simple: to take the natural sweetness stored by a plant and deliver it, pure and reliable, to tables around the world. That is what happens inside a mega sugar mill. And now, you know exactly how it is done. Modern factory technology has made it possible to transform a raw agricultural crop into one of the world's most consistent, pure, and precisely manufactured food ingredients, at a scale and efficiency that continues to improve with every passing year. From field to factory, from raw juice to refined crystal, every step of this process is a testament to precision engineering, continuous quality control, and the relentless pursuit of a product that is as pure, white, and consistent as science and technology can make it. Pure, white, consistent. This is the sugar that leaves a modern mega mill, and this is the remarkable process that makes it possible.